The same problem that we just did in the previous video was the integral of z, the triple integral of z, dv. And this triple, the only thing that we've changed is the region that we're integrating over. We're going to integrate between the same two planes, and only the piece between the two planes that we're going to integrate is the piece that lives over this half circle instead. Why? I mean, everything comes out to be the same initially. We do the z integral in the same way, and we're left with the same 3x plus 5y squared over 2 minus x plus y squared over 2. So once we integrate out the z, we're left with a double integral. We have a double integral. But now, what I want to point out is that we go back to double integrals now, and we do the double integral in the way that makes the most sense. In the previous example, we were doing a double integral over a triangle. We could have done that x first or y first. It didn't matter. We chose to do it y first. But now, we don't want to do this x first or y first because the functions are hard to deal with. We actually want to do the double in polar coordinates, because we're integrating over a semicircle for this double integral. So we do it in polar coordinates. We have an integral from 0 to pi. Theta goes from 0 to 180 degrees. The radius goes from 0 to 2, and it's the same radius everywhere throughout, right? If we're here, 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 it's the same radius from 0 to 2, so those are constant endpoints of integration. And then we have a 3 times r cosine theta plus 5r sine theta squared over 2 plus r cosine theta plus r sine theta squared over 2, and then we have the r dr d theta. Now we can do this integral too. This is going to be pretty nasty. We FOIL these things, and we'll end up with r squareds and cosines times sines for the cosine squareds. And then we'll have the extra r, so we'll actually end up with r cubes everywhere, and we'll integrate that to r to the fourth over 4. When we end up with cosine squared of theta, remember the way to integrate that is to write cosine squared of theta as 1/2 plus 1/2 cosine 2 theta, and then we can integrate. For sine squared theta, that's 1/2 minus 1/2 cosine of 2 theta. Very similar identity, just a different sign in there. And then we can integrate that. And for the terms, when you FOIL inside-outside terms, you're going to have sine times cosine. For these, we use a u substitution with u equal sine theta and du equal cosine theta d theta. So we can do this integral too. I'm going to leave it here because we know the steps to do this integral. And what I wanted to point out is that with a triple integral, once we've integrated in z, we go back to sections 16.2 and 16.3. We're back to a double integral, and we have to make the right choice for that double integral. In this case, the right choice is to do it in polar coordinates. Even though the integrals end up being messy, that's still the right choice, because it would be even worse if we were dealing with the square roots of trying to do this in rectangular coordinates.